We're going to look at another graph traversal method, which is called breadth first search, or BFS for short. So this is another technique for traversing a graph. So we're just going to visit every vertex and every edge of our graph, but in a slightly different order than if we were using depth first search. But we can still use the result of this in order to compute a spanning forest for each a spanning forest of our graph, which is one spanning tree for each connected component of our graph. So this will also give us a way to figure out what all the different connected components of our graph are, and if there's only one connected component, meaning our graph is connected. And breadth first search runs in linear time. That is here, big O of n plus m time, where n is vertices and m is the number of edges that we have. And we'll be able to extend this a little bit in order to solve a lot of other common graph problems, like finding a path between vertices and finding a simple cycle, just like we were able to do with depth first search. So how does breadth first search work? It again uses a mechanism for setting and getting labels on vertices and edges. So we'll have every vertex is initially marked as unexplored, and every edge is initially marked as unexplored. And when we encounter vertices, we'll mark them as having been visited. And for edges, we'll mark them as discovery edges if we used this edge to discover a new vertex that we haven't yet visited. Or, in the case of breadth first search, we're going to mark these other edges that are not discovery edges as cross edges. So this is our first difference from depth first search. And the reason for that is because when we encounter this non-discovery edge, based on how we traversed our graph, it'll mean something a little bit different than before. But again, this is just that this edge goes to a vertex that we have already encountered. Okay, so breadth first search, its first step is to set every vertex and every edge as unexplored. And then it will go through for every vertex in our graph that hasn't yet been explored, it'll call breadth first search on that vertex. Now, notice that we're only calling BFS from this location, and ultimately, just like we did with DFS, we're going to call BFS on a vertex from this side once for each connected component of our graph. So as a result of our call to BFS from the starting vertex, we'll mark every vertex and edge which we can reach from V. So every vertex which belongs to the same connected component as V. So how does BFS work? We're given some start vertex S, and we're going to create essentially layers of everything that we can reach from S. So we'll have first our layer 0. So this is our layer 0, which consists of only our starting vertex S. And when we add this vertex to our layer, we set it as visited. Then we're going to create from this layer another layer. So the first time we do this, this will be layer 1. And what vertices get added to this layer are based on all of the vertices that are adjacent to S. So for every edge that we have from S, and the first time here, S is the only element that belongs to this layer, we'll add a vertex to layer 1 if it's adjacent to S. And anytime we add a vertex to the next layer, we mark that vertex as having been visited. So all of the adjacent vertices to S are in the next layer. We add them to the next, as soon as we add a vertex to a layer, we mark it as visited, and then we appropriately set its edge to be either a discovery edge if this edge was leading to a vertex that we had not yet marked as visited, or we mark it as a cross edge if this edge is leading to a vertex that we had already visited. Now that we've formed this layer 1, then we're going to take this layer and use it to form the next layer. So that'll be layer 2 and in ascending order. Now how we form this one is we'll take every vertex that we had in the previous layer and consider all incident edges. If this edge leads to a vertex we've already encountered, again this is a cross edge, but if this edge leads to a vertex we have not yet encountered, then this is marked as a discovery edge, and we add that new vertex that we've only just now encountered to our next layer, and we mark that vertex as having been visited. Okay, so we're keeping track of each layer as we go along. We'll go through each vertex of the previous layer and every edge coming out of that vertex and mark that edge as either discovery edge if it leads to a new vertex, or a cross edge if it does not. If it leads to a new vertex, if this is a discovery edge, then we'll add that vertex to the next layer and we'll mark that vertex as having been visited. So anytime we add a vertex to a layer, we mark it as visited. Okay, let's see an example first. So let's say this is our graph. So notice that visually you can tell already this is not a connected graph. It has two connected components. But let's say that we start our breadth first search call at vertex A. And I'm going to mark vertices as this way if they've been visited. So initially just assume everything has been marked as unexplored. And we'll mark discovery edges this way with just a solid line. And we'll mark cross edges this way with a dotted line, with a dashed line. Oops. And notice again that we're talking about how to do these traversals on an undirected graph. We'll see later how we could apply the same ideas to a directed graph, but we're working with an undirected graph. As a result, we take these undirected edges and we assign a type of direction to them, not based on what existed in our original graph, because there is no direction in our original graph. We just give a direction to indicate how we had traversed it. So this discovery edge, this is directed because we had discovered this vertex, this destination vertex, by starting from this origin vertex. Okay, so let's say we start at vertex A and we begin our breadth first search with A. So we're going to add A to, this will be our layer 0. So whatever our starting vertex is our layer 0. And we mark A as having been visited. Now we're going to form layer 1. And I'm not going to draw it just yet because it's going to get bigger and bigger. But initially this is, we're going to go through every vertex of the previous layer, which is layer 0, and all incident edges coming out of it. So we'll start with vertex A, and we're going to consider incident edges B, C, and D, but we could pick any one of them. So in order to be deterministic about this, let's just say we pick the ones which go in alphabetical order. So we're going to mark this as a discovery edge going to B, and we add B to layer 1, and we mark it as having been visited. So this is our layer 1 so far. Before we continue, we're going to process the other incident edges. So now we'll mark this as a discovery edge from A to C. We mark C as having been visited, and we add C to our layer 0, layer 1. Now we mark the edge from A to D as a discovery edge. We mark D as having been visited, and we add D to our layer 1. Now layer 1 has been completely filled. We know that there's nothing else to put in here because we've processed every incident edge coming out of layer 0. So now we're going to move on to layer 1. So let's now process these in the order in which we had added them to layer 1. So this had gone B, C, and D. So let's go with B. And we'll process each incident edge of every vertex in layer 1. So first, we're going to mark this edge from B to C as a cross edge because it leads to a vertex we've already marked as visited. And we're going to mark this edge from B to E as a discovery edge because we haven't visited E yet, but we're going to visit it now. And we're going to add E to layer 2 because this is something that we could reach from a vertex of layer 1. Now the edge from C to D we mark as a cross edge because we've already visited D. We'll mark the edge from C to E also as a cross edge because we've already visited E. And then from C to F, this is a discovery edge because we haven't visited F yet. We're going to visit F now, and we add F also to layer 2. So this is what our layer 2 looks like next. Now we have one other incident edge coming out of layer 1. We mark this as a cross edge because we've already visited layer F. Okay, now that we've processed all incident edges from layer 1, we move on to layer 2, and we're going to form layer 3 using the vertices of layer 2. So from E now, since we had added these E and then F, we're going to go in that order again. So from E, all incident edges, we have only one, which goes to J. Now we're going to visit J and add J to layer 3. Now we have no other incident edges coming out of layer 2, so we're going to use layer 3 to form layer 4, but there are no incident edges coming out of layer 3, so this is our indication that we're done. There are no other vertices that we can visit. So our next step is to, now that we've finished our breadth first search call from A, we've exited that. Now we're going to check to make sure that we've really visited all vertices to make sure that we haven't missed anything. And we'll kind of go through in order here. We have A has been visited, B, C, D, E, F, these have all been visited. G has not been visited. I'm just going in alphabetical order here. This is just any arbitrary order of vertices to check that they have been visited or not. And this is when we realized that there was a connected component that we didn't reach. We visited everything which was reachable from A. We visited this connected component, but we still have another one. So now let's say we call breadth first search from G. So now we're going to form another layering scheme here, beginning with G. So we'll mark G as having been visited, and we're going to add it to layer 0. So this is a different layer in a different breadth first search call. And we're going to mark this as a discovery edge and visit H. We're going to mark this as a discovery edge and visit I. Both of these vertices get added to layer 1. Now we'll mark this as a cross edge, and we have no other incident edges coming out of this, so we would form layer 2 using any vertex which we can reach from layer 1, but since there isn't any, then this is our indication that we're finished. We have no other vertices that we can reach from vertex G. So now that we're finished with our breadth first search call to G, we're going to continue on checking have all vertices been visited. G, H, I, J, we've checked all of them. They've all been marked as visited, so we're finished. Now intuitively, breadth first search follows the same traversal as waves would in a pond when you drop a stone into it. So first we visit everything which is reachable within one edge of our starting point, and then within 2 edges, and then 3 edges, and so forth, working our way out kind of from the starting vertex or where we drop a stone in the pond. Or another way of looking at this, this would be maybe the order in which you would invite people to a wedding. First, you invite the people closest to you, and then kind of work your way out.